We've been talking about big idea 2 for a little while now. We did it with atomic structure, and in this chapter we're going to get into bonding as well as molecular geometry. We'll review how to draw compounds, single, double, and triple bonds. We're going to take it a step further this year. We're going to get into expanded octets. We'll also be talking about more shapes than just the linear, bent, trigonal, pyramidal, trigonal, planar that you learned about last year, as well as tetrahedral. We're going to be looking at about 20 different shapes. You'll be building compounds in the lab, taking a look at their shape and also their hybridization. Nothing that difficult, but everything requires a lot of practice, which you will get this week. So same learning goal we've been talking about. We're going to look at the forces that link atoms together to form compounds, and in a subsequent chapter we'll look at the forces between them, the intermolecular forces. So we're going to introduce bonding here. You're going to see a lot of review from honors, and that's good. You always like review because that'll be easy for you. And then we'll make it a little more difficult. But again, if you take the time to practice, you'll be very strong here. Chemical bonds are just forces that hold atoms together or ions together. And don't be confused there, because what you're used to might be something like this. This would be methyl chloride, and you will recall how to draw the structural formula from last year. And you recognize this stick as what? Single bond. The Doritos have to go. I don't know who has them, but the Doritos have to go, please. This is a single bond. This is a covalent bond. Remember, in a single bond, you have one shared electron pair. With covalent compounds, you're going to have 2 or more nonmetals that link together through covalent bonds, sharing of electrons. In an ionic bond, for example, if you had sodium iodide, you have a transfer of electrons. Sodium loses 1 electron, forming an iodide ion that has gained sodium's 1 lost electron. You still have an electrostatic interaction between the 2 ions, and that is a bond as well. So bonds can be covalent or they can be ionic. We'll get into nonpolar versus polar covalent in a little bit. Remember, with your ionic compounds, you're going to have metallic cation, nonmetallic anion, and with your covalent compounds, you're going to have 2 or more nonmetals sharing electrons between them, whereas in your ionic compounds, metal, nonmetal. The only thing you really have to be careful with is typically if you have a polyatomic ion, let's say you have sodium sulfate. This is an ionic compound, metallic cation, nonmetallic anion, and you have a polyatomic anion here as well. What you have to be careful with is hydrogen. If you have hydrogen sulfate, for example, this is covalent, all non-metals here. So you can have polyatomics when they hook up with H, it's covalent. Be careful, that's a common mistake kids make. And I know there was a question in regard to it last year on an AP exam. We'll take a look at it in a bit. So covalent versus ionic. In an ionic compound, you can actually calculate the energy of interaction between a pair of ions, and we can do so using Coulomb's law. We'll take a look at that in a little bit. When you've got nonmetals combining, you've got covalent compounds. And remember, The reason why compounds form, the reason why ions form, they will lose, gain, or share, in the case of a covalent compound, to have an octet of electrons in their outermost shell. They want to be isoelectronic with a noble gas. And the octet rule states that elements will gain, lose, or share electrons to achieve this noble gas configuration ending in NP2, NP6, in which you have 8 valence electrons. Not all elements form an octet. For example, hydrogen just forms a duet. So 2 valence electrons when it is in a compound in a shared situation. So for example, if you have hydrogen chloride, and again, be careful with hydrogen, typically named in an ionic fashion, but this is of course a covalent compound. The chlorine component has 2, 4, 6, and there's 2 electrons in that shared pair. And I'm going to review how to draw these with you. Some of you will remember, you were excellent at it last year. Chlorine has 7 valence electrons, and we'll review how to draw these, don't worry. Hydrogen has 1. So chlorine has 1, 2, 3 lone pairs of electrons, and this in the middle here, you have 2 different colors, is a shared pair of electrons, and we can represent a shared pair of electrons as a single bond, the single stick here. But what you can see here around chlorine is that there's 2, 4, 6, 8, an octet of electrons. Hydrogen has a duet, 2. Most will form an octet. There are a few exceptions, and there are some atoms you'll see this year that can expand their octet, and we'll talk about that next time. Most of you, I think, will remember how to draw Lewis symbols for atoms. For example, if you had some generic element X, X represents the chemical symbol, the nucleus, and the core electrons of the atom. There are 4 seats, if you will, like little bench seats, where valence electrons can be placed. And these are the dots. I typically start right here, then here, here, then here. 1 electron in each orbital until pairing occurs. So 5, 6, 7, 8. So for example, if you look at magnesium, silicon, and phosphorus, you should recall that for the main group or representative elements, that's S or P block elements, the group number corresponds to the valence electrons. So magnesium's in what group? 2. 2 valence electrons. 1, 2. And it doesn't matter what side I start on, I just don't want to put 2 together. 1 on each side, so you have to pair. Silicon group 14 has how many valence electrons? 1, 2, 3, 4. Phosphorus group 15 has? And you can double up wherever you want. Doesn't matter. Should really double up in the S and then leave the P, 1 with each, as you learned about. Pretty much all review. Yes, yes? Almost excited like this is going to be easy, right?
Nope.
Today's is easy. We'll mention very briefly your ionic compounds, although we're not going to really play with them very much here. We'll come back to them in a subsequent chapter. I know. Why don't you go wash your hands or get some Purell, let them dry. That's yucky. I have wipes over there if you want. With your ionic compounds, ionic bonds are going to hold ions together. It's an electrostatic force. And what you're going to get is a whole network. An ionic crystal has a distinctive repeating pattern of particles. And you can see, for example, sodium chloride table salt right here. And I've also got sodium chloride on my benchtop right there, where the ions are at distinct points and the electrostatic interactions that form between them. Sodium chloride does not have one sodium ion and one chloride ion only. That's the simplest whole number ratio. You'll actually see that each sodium ion is going to strongly attract 6 neighboring chloride ions and vice versa. And what you get is this cluster of ions, and it's quite extensive. Other ionic compounds are shown here. You can see them as well. You can actually use Lewis symbols to show how ionic compounds form. It's not something we do very much of. I'll mention it here. The example I gave you was barium iodide. Everybody knows how to formula, right? With ease, so if my honors kids ask you, you should be able to do it. And it might be a good way to get volunteer hours because some of them could use some help. Barium, of course, has a 2+ charge as an ion because it's in group 2. It loses its 2 valence electrons to form an ion. And for every 1 barium ion, you're going to have 2 iodide ions. You need electroneutrality. And the interaction between the ions will essentially form an ionic bond. We don't do that much representation Lewis structure-wise with ionic compounds, but it's not difficult at all. Whatever you have 1 of typically goes in the middle. If you have 2 and 3, it's a little more complicated. What is important is the next piece. It'll become critically important in a subsequent chapter, but we'll introduce the concept here. You can look at energy changes that occur as ionic compounds form. We refer to the term either as lattice energy or lattice enthalpy. Initially, it was referred to as coulombic attraction. And then in subsequent AP exams, we've seen it written more as lattice enthalpy. So just be careful there. They're all synonymous, but we're seeing lattice enthalpy now. It says the energy of formation of 1 mole of an ionic solid from its separated gaseous ions. So you're forming 1 mole of solid from its separated ions in the gaseous state. Keep in mind, ions are typically aqueous. It is exothermic, highly energetically favorable. You can't measure it directly. You do so doing a Born-Haber cycle that is far too complicated than anything I want to talk about. But the electrostatic forces are governed by Coulomb's law. And Coulomb's law you've seen already. It says the attractive force is proportional to the magnitude of the charges over r squared. That is the distance between the ion centers. Let's think about this. So force is equal to the magnitude of the positive charge times the magnitude of the negative charge all over radius squared. So if you were comparing, for example, sodium chloride with magnesium oxide, the force of attraction between magnesium oxide would be significantly greater than sodium chloride. Your first criteria is the charge, 1 plus, 1 minus, 2 plus, 2 minus. So the magnitude of the charge in magnesium oxide is greater than that of sodium chloride. Hence, this is going to have greater lattice enthalpy, greater coulombic attraction. These bonds are going to be stronger than these. If, for example, you were comparing 2 ionic compounds that both were 1 plus, 1 minus, now you'd have to consider the radius. Now, sodium ion in both, chloride ion versus iodide ion. Which ion has a larger radius, chloride ion or iodide ion? Iodide ion. And in the back, I immediately saw some of you looking at the periodic table, which is absolutely the way to go. You know that iodide's ion is larger than chloride ion's radius. Why? Yes, and if you write lower period on your quiz, you're going to get no credit. You really need to be specific. What you're looking at is that iodide's valence electrons are in the 5th shell, farther from the nucleus, with more electron shielding than chloride ions' valence electrons in the 3rd shell. Be very, very careful. You really need to specify or clearly state your reasons. Be careful. So iodide ion has a larger radius, and you can think about it this way. Here's sodium, here's chloride ion, which will be bigger. Here's sodium ion, and here's iodide ion, which will be larger than chloride ion, maybe not drawn to scale. This is like two skinny kids giving each other a hug. They can get pretty close together, right?
Yeah.
Well, here's a skinny ninny, and maybe here's a mommy who's about 4 or 5 months pregnant. You can't hug her as tightly because she has a pretty big middle. So clearly, the distance between these two ions will be greater than this. With the increase here, you get a decrease in Coulombic attraction. Think about it. How many of you have baby siblings or younger siblings who are maybe like 8 years younger than you?
8?
Yeah.
That's a lot.
I know it's a lot. How about 5? All right. So if they were about 5 years younger than you, maybe when you were like 6, 7, 8, and you wanted a hug from, well, no, you'd have to be 5. That's why the 8 works better. All right, fine. So you're about 4 or 5 years old, and mommy is pregnant, and you're not giving her the same big bear hug that you used to, right? Because her midsection's getting a little bit bigger.
My mom was pregnant with twins.
Well, she was even bigger then. Same concept, all right? So two skinny ninnies can hug each other really closely. Here's a skinny ninny and a prego mom, and you're not getting as close. Easy concept, go with it.
So the sodium chloride has the greater lattice energy?
Yes, because the radius is going to be smaller here because the atoms, or ions in this case, can get closer together with the decrease in radius, increase in Coulombic attraction, increase in lattice enthalpy.
What if you had like magnesium oxide and sodium phosphate?
Well, sodium phosphate,
It would still be.
no, I know where you're going with this. So if you had sodium phosphate, you have 1 plus and 3 minus. And it's charge. So in this case here, you've got 4 versus 3 because you're multiplying. And these two are going to get closer together because a phosphate ion is going to be pretty hefty in size.
I wasn't thinking that you were multiplying.
Yeah, so maybe you're thinking something like aluminum chloride, 3 plus, 1 minus. So this would both be 3 on top, and this radius is going to be larger. That's going to be a pretty big ion, but it's a good question.
No, that was test.
Well, you already have, 1 phosphorus bonded to 4 O's. So you've got 1, and then so it's already increased just because of the atoms alone. I don't think you'd get anything so nitpicky there, but it's a good question.
Like aluminum chlorate, because chlorine has a bigger radius than.
But chlorate has Cl covalently linked to 3 O's and a charge. So that's I would think the polyatomics will always be larger. You have multiple atoms there.
Maybe if you had chlorate and phosphate.
Oh, I thought you were comparing this. That probably would be hard to tell. They'd probably have to give you more information. They'd have to specify the radius of the ion in that case. So don't make it hard. Everything in chemistry is super hard, and your thinking line is ridiculously high level, which is good, but I think you're making it harder than they'll even make it for you. But it's a good question. All right, so what you're seeing here, it says larger charges mean stronger bonds because of the increased interaction. So calcium chloride would have stronger bonds, stronger ionic bonds. How come? Why would calcium chloride's bonds be stronger? You have 2 plus and 1 minus here versus 1 plus, 1 minus. You don't care how many of each you have, just the charge. Now with the smaller ions, as I said, if you have 1 plus, 1 minus, you got to look at the radius. So look at this problem. It says, which of the following has the greatest lattice energy or enthalpy, or it could say coulombic attraction? I really feel that you will see a question like this for sure. They love this, and the term will say lattice enthalpy. So what do you think?
Magnesium sulfide.
Magnesium sulfide because 2 plus 2 minus for 4, exactly. So go with the charge first. Go with the charge first before radius. Only go to radius if you have the same charge. So if you had potassium chloride and cesium chloride, which would have the greater lattice energy? The one with the smaller radius, and that would be potassium chloride. Be careful there. Tricky, tricky. All right, where we're really going to focus is on covalent bonding. We're going to review how to draw the structures, probably in much more detail tomorrow, and we're going to introduce a lot of new type of drawing. Not difficult. You have a solid, or should have a solid foundation, but like everything else, it requires a lot of practice. You have to draw like crazy to really perfect drawing. It's fun. The kids like it. You'll get practice in class. You'll get practice in the lab, but you've got to practice, practice, practice. All right, with Lewis structures, we're going to combine Lewis symbols for atoms such that we generate compounds. We're going to show how bonded atoms typically have the same electron config as noble gases. For example, if you had chlorine gas, molecular formula Cl2. If you drew the Lewis dot structure, I'll go over how to do all of this in great detail. I just want to go over a few key terms here. My 7 valence electrons for chlorine. Seven valence electrons for chlorine here. In the middle, I have my 1 shared electron pair. Those are my bonding electrons. These are my non-bonding electrons, or my lone pairs of electrons. So just some terminology I want you to be familiar with. Some other key reminders. With your nonmetals in the second period, except boron. Boron is an exception. Beryllium is an exception as well. Typically, they tend to form the number of covalent bonds equal to 8 minus their number of valence electrons. Fluorine's in group 17. How many valence electrons? 7. 8 minus 7 is? 1, and fluorine will form one single bond. Your halogens typically form 1 bond, 3 lone pairs, although you'll see a lot of exceptions to the halogens this year, but not fluorine. Oxygens in group 16, how many valence electrons? 8 minus 6s? And oxygen typically forms 2 bonds, 2 lone pairs. Nitrogen is in group 15. 8 minus 5 is 3. Nitrogen typically forms 3 bonds, 1 lone pair. Carbon's in group 14. 8 minus 4 is 4. Carbon forms 4 bonds, typically no lone pairs. Carbon monoxide's an exception. We'll take a look at that one.
With like H2O, isn't it? Like the lone pairs are like not exactly on top and bottom.
What you're looking at there, for example, if you had water, if you just drew it crudely, you'd have this. But what you're remembering from last year, which is wonderful, no it doesn't, is you're remembering something called Vesper, and it has a bent molecular geometry with a bond angle of 104.5 degrees. Your 120 would be trigonal planar. I'm not sure, but maybe something like this. That would be 120, but we'll get into all of this as the week goes on. Now, typically what you're looking at here is with a shared pair, 1 electron came from this chlorine and 1 electron came from this chlorine, or if you had hydrogen fluoride, one of the shared electrons comes from fluorine, 1 comes from hydrogen. So typically in a shared pair, each atom contributed 1 electron to generate a shared pair. That's not always the case. I'm going to show you this here. I'm not going to see all that much of it, but I'll mention it. When you form a hydronium ion, H3O+, or an ammonium ion, NH4+, what happens here is that the shared pair actually came either from a lone pair of oxygen or a lone pair of N. And this forms what's known as a coordinate covalent bond. For example, if you had a proton that's lost its electron and water, and I'm going to draw water like this so you can really see how it smacks on, you can form a hydronium ion. Polyatomic ions are in brackets with the charge outside, and essentially this lone pair or non-bonding pair now becomes a bonding pair. So they didn't each contribute 1, it just came from the oxygen, and that's a coordinate covalent bond. And you would see the same thing with the formation of an ammonium ion between a proton and ammonia. As such.
Wait, if you do that, isn't there 3 electrons?
Huh?
Well, like, if there's already 2 paired electrons there, and they're adding, are you adding 1?
No. essentially these two electrons now just form a bond between the H and the O here, but you still have 2, 4, 6, 8 octet, 2, 4, 6, 8. So this lone pair gets shared with the H. And it's just called a coordinate covalent bond. I don't think it's going to affect you very much. We also have multiple bonds, for example, and we're going to review how to draw all of this. If it looks foreign, don't worry. For example, if you had carbon dioxide, I'm sure you remember how to draw carbon dioxide. And you'll see why I put the electrons there in a couple days. This is a double bond, and a double bond is 2 shared electron pairs, or something like nitrogen gas, where you have a triple bond holding the 2 ends together. What do you think is stronger, a double or a triple? Triple, for sure. That's going to be stronger and shorter because the bonds get a little bit twisted. Very briefly, I want to review electronegativity with you. You know from our previous chapter that electronegativity is the ability of a bonded atom to attract bonding electrons to itself. This is based on values. Electronegativity value of hydrogen is 2.2, fluorine is 4.0. The higher the electronegativity, the more it pulls the bonding electrons toward it. It doesn't transfer electrons, it's just an unequal sharing. And what you create here is a dipole. It shows the unequal distribution of electrons. The more electronegative atom, which is fluorine, fluorine is the most electronegative atom, acquires a partial negative charge. And the less electronegative atom acquires a partial positive charge. It's not a transfer of electrons, it's an unequal sharing. And you should recall from our previous chapter that as you go across the periodic table, what happens to the electronegativity? It's going to increase, and down a group it will decrease. Okay? I don't really think we need to do these problems again. You've seen all of this before. The other thing I want to remind you of are some bond types, and I've got a really good Pogel packet on this that goes into it in great detail that I think will help you greatly. When you're considering bond types, we've got ionic and we've got covalent. With ionic bonds, remember, you're going to have a metal, non-metal. You're going to have ions. You have a transfer of electrons. For example, sodium fluoride, in which you have a sodium ion, fluoride ion 1:1, simplest whole number ratio. In covalent compounds, you have nonpolar covalent, we'll abbreviate NPC, and you have polar covalent, we'll abbreviate PC. In a nonpolar covalent, you have electrons are shared equally between atoms. And in a polar bond, electrons are shared unequally between atoms. So for example, whenever you have two of the same, like H to H, or if you have Cl to Cl, or F to F, all nonpolar. But you also find that, and a good one to know is C to H. These are going to have very small differences in electronegativity. For example, carbon's 2.5, hydrogen's 2.2 for a difference of 0.3. Typically, an electronegativity difference less than 0.5 is going to be nonpolar covalent. They're not going to give you values. The one I would absolutely memorize, these are obvious because they're the same. C to H as nonpolar covalent will help you greatly. When you have large differences in electronegativity, for example, anything to fluorine, these are polar covalent bonds. And again, they're not going to give you values. It's really important that you know the trend. There is a question here in your notes. I'm going to change it around a little bit so it serves you better. You'll see questions like this in your homework at the end of the chapter, and anybody can subtract two values and look at a chart. But the real question is, can you do it off the periodic table? For example, if you had carbon binding to N, O, or F, which bond would be most polar? C to F, because fluorine's the most electronegative element. If you had H to N, H to O, H to F, which is the least polar? Right, that's what you want to be able to do. And like I said, C to H being nonpolar will be critically important. And I showed you how to depict those polar bonds. The last thing I want to do with you today is review some key terms, and then next time we'll get busy drawing the compounds. I just want to review a couple of key terms. I think you will remember them from last year. For example, molecular formula. That will show you the atoms that make up the compound as well as how many of each you have. So for example, molecular formula might be CH3, Cl. 1 C, 3 H's, 1 Cl. A skeletal structure shows you the arrangement of atoms, and I'll review how to figure this out next time. A structural formula shows you not only the way the atoms are arranged, but also the linkages and the lone pairs of electrons. The term isomer I will hit next time. A central atom must be bonded to at least two atoms. Typically, the central atom has the lowest electronegativity. We'll talk about how to draw oxyacids as well, where H typically hooks to O. That's a common mistake. Typically, your molecules and polyatomic ions will have compact symmetrical structures. For example, fatty acids typically don't. And the last thing I wanted to mention is if C is a central atom, what would we call the H's and the Cl? Those would be terminal atoms there at the ends. Please remember that H will always, 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 always be a terminal atom. That is a very brief introduction to bonding. I have a series of sheets for you that I would like to give you. I highly recommend that you take the time tonight to look at types of bonds. I think that will help you a lot. And I'm going to give you all the sheets at this point.